Good afternoon, YouTubers. Today we're going to be studying some wind turbine, in particular, those kind of shown here, particularly this one, the Savonious type of vertical axial wind turbine. And so this is the one that we're going to be studying. There's, as you can see, there's basically three models. The horizontal model, which are typically the one that has the tall pole, and they are very efficient in capturing wind. And then we have this Darius type of vertical turbine, which are basically a combination between this type of turbine and the Savonious. So this is a kind of in what I will say, not in the middle, but somehow, that's what it means. They are still on the vertical axis type of wind turbine. So as you can see, we're gonna be again studying this one because it can be easily done, constructed, and I want to figure it out how efficient it is. Now, going into a little bit more of details, the power capture or the power within any given wind speed can be calculated through this equation. Now, the coefficient of the power coefficient shown here depend on the blade tip speed, and without these, if you are 100% efficient, you can capture a lot of energy as shown here with a lot of power. Now, as soon as you are trying to capture that energy, there's going to be a drop in efficiency. And it's interesting, a guy with the last name Betts said that the maximum amount of energy that can be captured or power that can be captured from a turbine, a wind turbine, would be limited by this curve here. So the maximum will be somewhere about, I was close to 60%, no more than that. And depending on the type of blade design, you are somewhere here. Like for example, Savonious, that's the one that we are interested. It got this kind of an interesting curve. And there's the American multi-blade, which is used more for water extraction and so forth. So there are different design that goes again depending on the blade tip versus the wind speed. And so we'll see how that will go. In Savonious type of rotor design, there's I've seen several, and the one that I'm gonna be more interested is on this one. This one, air will be captured by this blade, and if it's captured by that blade, it will turn through to the second blade, and they will allow to increase torque by that action. And so what I mean by that is this is more into it. As you can see, they look more like one of those oil barrel design, and these are two of them, one in top of the other. So more like I want to make a big difference between this design and this design where that gap is not available. So this is two blades, no gap. This is four blades, no gap. And could be a big difference between the blade tip speed versus this one here. And going back, so this is more into it. This is like with 55 gallons type, which is very closely related to what I have done in Solidworks. This is not. There's no gap, and this is going to drag, and so this is going to drag as well. So it will turn. If wind come this way, it's going to turn counterclockwise. That's how this will work. Could be more into it, like for example this one that has a double, and they are stacked one on top of the other. And this is kind of cool because this avoid situation in where you might have a very small breeze, but it cannot be captured because the bottle are not properly directed to capture that wind. Having this kind of two design, 190 degrees, rotate against the other, that will allow that always you will capture air, and that's good. But again, what I'm gonna be designing is more like this, based on the dimension of a regular kind of a drum, a 55-gallon drum. So let's go to Solidworks and see what we can do back there. So this is my design. This is not a video about how to put this together. It's more like what I did. And So basically, I have the Savonious blade right there, a rotating body because definitely I will be doing flow simulation to measure torque and so forth. A wind tunnel, so you have a wind tunnel here, and you have the proper lead as required for SolidWorks to do proper flow simulation. So this lead will be the incoming air, and the air will pass through the Savonious turbine and will go into an atmospheric pressure here on the other side of the tunnel, the wind tunnel. Now, very simple to do this. Basically, you start with a sketch here, and let's take a look at that sketch. And that sketch basically is for the bottom lead of the Savonious, which is about a meter, 1.1 meter in length. And with that, then we move to where we are here. That I did that. You move to this one. This one basically is how I design. As you can see, they are tangent to the big circle, and they are slightly larger. I mean, this is half a drums. They're larger than the 24 current type. I think that is about 27.8 or it's about 28 inches. So you got both of them with a gap here. So air, if this is capturing air, air will go through and will go through this one as well, and we escape that way. So that will create this counter, in this case, if you're watching from the top, this clockwise rotating situation. Let's see. We are out of here. And the next thing is after you extrude this guy, let me put this back after you extrude them, that's basically what you see here on the extrusion. Then you extrude one first and you hollow them, with the shell, and then you extrude the other one and so forth, and eventually you combine the whole thing, and that's what I did, combine the both of them so everything looks one piece. And eventually you start to work on that sketch there is for the rotating body, so that we can analyze this in SolidWorks. And finally you have here the box for the tunnel. I believe that I did this kind of too short, maybe it should be longer. We'll see that on the results, and that I will show you in a second. And eventually you need to go to flow simulation here, to tools, and to put these two together. So that's what I did on here, create leads. So let's move from here and let's analyze. Again, this is basically the size of a regular 55-gallon drum cut in half. That's it. So now let's move to flow simulation. If you don't happen to have this tab, I mean, you can get that tab right from here, add-ins, and then check whether you have it or not. Like for example, where is it? Is right here. All right, Solid Flow Simulation 2022. That's the version that I'm using on SolidWorks. So I'm out of here, and that's the idea. So let's go to flow simulation. I already did several runs, and I only want to show the runs and the results. This take a while to get it done. So we go here, flow simulation, tab here, and there's many things down here. Let me start very simple by establishing the parameters accordingly. Like for example, the first thing that you need to understand is what is the rotational region here, and right now it has a defined value of 116 RPM. Notice it that it is extremely important that you understand that negative is because it's rotating. You see that arrow there is rotating clockwise, because air is coming from this wall, hitting this part of the blade here, and it's spinning the blade or the turbine this direction. So meaning that this negative value here, the 116 negative, is in the proper direction of wind speed. So if the wind speed increases, probably this number will increase as well. Now, check that the torque here, which is this arrow here, that's the positive torque. And if you use your right hand rule, you will notice that if you are following this arrow here, the one that is showing the direction of spinning, your torque will be negative because it's against this arrow. This arrow will mean uh, if the spinning were counterclockwise, oh yes, then you will have a positive torque. At this point, it's a negative torque. So this value here of minus 116 will provide basically a negative torque somehow, right? That's what it means. Now, so you establish where that number comes from. Out of the blue? No. That number comes from another study. And let me get out of here for a second. That number come out from this goal optimization tool. I did several goal optimizations. I did a what if analysis, and I also did a goal optimization tool, which is the most important thing when you start to understand what you did. Like for example, that goal optimization tool is this, in where you establish at least, for example, at minus 50 RPM, I get a negative torque. But if I apply 500 RPM, I get a positive torque. It means that I'm adding energy. For the turbine to spin at the current wind speed at 500 RPM, I will have to add energy, in that case torque. On the other hand, if the turbine is spinning at minus 50 RPM, then I'm getting some torque out. I'm extracting some energy with a negative value of 57. Now, between those two values, if you allow for the goal optimization step here, as shown here in this analysis, remember you can do several here, but the one that we are talking about or targeting is goal optimization. So you know the torque that you want. In my particular case, I want zero torque. When you have zero torque, it means that you are not adding energy to the turbine, and you are not extracting energy from the turbine. So the turbine will do some kind of a free spinning at the given wind speed. In this case, you can see that after the first 2 points are done by the user, this third point is calculated by the Solidworks, probably kind of a Newton-Raphson type of algorithm. And then since I have a torque here of a negative torque, it knows that I need to increase RPM for the blade, and it starts to increase it to 116. Again, is getting 220, but it knows that at 500, so you need to still move to the positive. While this is negative, it knows that I need to move to the positive side. So it's moving to the positive side by increasing the RPM. Then it get to a point, like for example, at 242, now it's positive. It's almost nothing. There's no torque there at 242. But it knows that it's a positive 0.02. However, my for this system, I set the plus minus to less than 0.02. So it went from here to here. And let's see what we got there. So eventually this was not good. Point number 10 was below 0.02, definitely. So these are the RPM that this turbine will spin, where you are not extracting energy, you are not adding energy to the system. So it's about 242. In order to extract good amount of energy, you want to look for the maximum torque here somewhere. It seems like that torque might be somewhere here. Between, I would say maximum torque somewhere is happening here about 116. Which is very close to lambda of 1.1. Remember that lambda is the ratio of blade tip speed to wind speed, and that value is approximately 1.1 for what we have seen here at 116 RPM. Alright, so that gives you an idea what somehow how important it is to get the goal optimization, because it definitely will allow you to understand better your turbine design, in this case the Savonious. Now, one important as a final aspect of this, I also did run a complete run by fixing the turbine to 116 RPM. in this case, I was able to do many analysis and things of that nature, which kind of surprised me. I will say this flow trajectory here, let me show you how that looks like. When you take a look to that, you can see that at 116, it creates sort of a vacuum that it kind of pull air or wind from this side and wind from this side, which is okay. But I was not expecting that it pulls wind from this wall as well. So it might be that this wall is too close, should be farther away. I don't know, maybe that's something that need to be checked. Now, if the wind on this wall is about 13.6, you can see that this can go very high. There's something here, this turbine, that is causing some of the wind speed to jump to about almost 100 miles an hour somewhere inside. And you can see some of that red right here. Some of those lines are red. So that's kind of interesting. I never thought about that would be happening. And it's kind of strange that on this Savonious turbine is predicting winds inside so high, because the one way to check that out is with cut plots, and we can go back here. I put some of those cut plot right here in both directions. Like for example, let me get this out of the way. Let me get this, let me hide this. And now let me get this cut plot and let me show that. And you can see on that cut plot that there's a very amount of red, meaning high speed here, about 80 or so. Let's move these and you can see the different, like, still, I mean, how can you get here wind so high? That's very interesting. See how that looks like? How that red spots stay there in the 80 miles an hour. And deep inside, you have very low wind speed in the neighborhood of 16 or so. Then you get the red, the yellow, the green. The green is about 40 something miles an hour. So that's, I mean, to me, very, I don't know, interesting result. Need to be checked. And I will continue doing some testing and at the level of flow simulation before doing anything in real. But you know, it's very strange that I get those wind speed based on the fact that the maximum wind speed that I'm using right now from this wall is about 13.6. So now that's that way. Let me get this off. Let me hide that. Let me get the other one, this one, so that we take a look at this one. This is on the Y direction. So again, you can see what is happening on the Y direction. And again, the red and the yellow and the green indicating very high speed near the, you know, in the vicinity of the turbine. But you know, far away from the turbine, there's not much going on. I mean, but again, still kind of, I'm very curious why of this kind of result. Might have to do with the, perhaps with the mesh that I was using. Remember that for this guy, for the turbine itself, I use a very fine mesh, and I'm gonna show you that in a second. But for the everything else, for the wind tunnel, very you know, I stay with a value of 3 for the mesh, regular mesh size. So let me show you that. So let me get out of here. And now let's show you the mesh, how that looks like right here. See, for the, let's see where we are, mesh 1. For the, this mesh is for the turbine, for the solid itself. See how tiny it is. So I want good definition around the turbine. So now for the rest of the system, I use what is they call here basically on the global mesh. So basic, that's it. You see how large it is. Maybe that's creating another problem that I need to figure it out. whether I can survive with this mesh of 3, or I need to increase it at least to 5. Now, every run at the current size right now takes about 10 minutes. If I increase this, perhaps the global mesh to from 3 to 4 to 5, then that will increase the time definitely to 20-30 minutes per run, and that's a lot of you have to leave this overnight perhaps running. I'm using an i5 computer with a microprocessor i5, so it's not the fastest machine in the world. Get some of the job done, but still be careful with that. So let me show you here global mesh. Let's see, edit definition. You see, not much there. It's about 3. That's all what I'm using. If you increase it to somewhere here, that will take for a while. On the other hand, the other thing that I did was in order to get result that I start to believe them, was when I got the local mesh, and I increased that local mesh from 0 in both to 5. You see, you can still do better. You can get to 9, but that's very tiny what you will be watching here within the refining those cell sizes. Like for example, that one level of refining for the fluid cell, and that's near the solid, in this case the turbine, and this the second one is level of refining cell of fluid and the solid boundary. So that gives you an idea with those where we are on this Savonious testing of the fluid flow dynamics and how that will looks like. So I'm out of here, and let's see what else we got here. Mesh. There we go. Now, again, that's basically it. It's kind of predicting, we'll say, roughly the numbers start to look good in terms of watt production at the wind speed of 13.6. You can tell that by the data that I did here on the goal optimization. If we take this data to Excel, then we can analyze the torque and the RPM, and with that information we can get watts. I did that, so let me open up that here. There we go. So basically, at a wind speed of 6 meters per second, because that's the wind speed that I'm using, in miles per hour it will be about 13.6 miles an hour, kind of a breeze. And here are the results from the Solidworks flow simulation at different RPM. And again, minus 50 and 500, you get these two values. So you know that there's a value of RPM between these two that will be 0 torque, which is this one here, about 0 torque. And that gives you about 242. So this turbine will do free spinning at 242 at a wind speed of 13.6 miles an hour of 6 meters per second. Now, if you change the angular velocity to rad per second, you get that. Now you multiply this rad per second by the torque, which is Newton meter, you get watts, and here's the watt. So obviously you can't turn the turbine at 500, because then you will be adding about 512 watts to the system to get that done. You want to extract energy, that's what you really want. So by extracting energy, you can see that the maximum amount of energy that can be extracted might be between 116 and 186 RPM, which is about 30 and 26.8. So this number can be demonstrated by other wind theory, and that makes a lot of sense. So they're about, I would say, about 20% efficiency of Savonious turbine that I designed here. So that will agree with the theory. And as you start to increase the RPM of the turbine, then obviously the amount of energy extraction will be less and less until almost nothing. So here's I would say, here's the sweet spot to get as much energy as you can produce, which is not much. It's predicting a number around, I would say, at the best 30 watt. So But again, wind speed is a breeze. I'm not talking about anything faster. Like for example, maybe you want to study what will happen at 12. You see, and but at 12 meter per second, that's a lot of wind. So, but remember, this Savonious is basically will be installed perhaps over a house roof, something like that. So it's not going to be very tall in terms of like a horizontal wind turbine. In this case, this vertical will be very close to the ground, where the wind speed are small, and that obviously will produce small amount of energy as well, which to me is so tiny. This is for basically for a drum design, something like this, like you know, like like this one. So that's how much energy you will get. About 30, no more than 30, around 30 watts. That's it, 30 watts. If you are lucky. Again, I'm not counting losses, gear reduction, or whatever you need to do to transfer this into usable energy. I'm only saying that this will have a torque of about 2.2 if you extract energy from this type of wind turbine, the Savonious style. It will look more like this. So that at 116 RPM you can extract about a torque of about 2.2 for a total of 26. So you can have a range between 116 186, and that will give you about 30 watts. Yeah, can you get another number here? Yeah, definitely you can. Like for example, what will happen at 200? Will the torque, remember there's a correlation here. Yeah, the torque drop, but the RPM got increased, so it means that you can pull a little bit more of energy, like in this case. Now if you get to a 229, the torque is so low that now you start to drop back again in terms of watts. At 229 you produce only 9.6, because although the RPM is high, but the torque is almost not there anymore, so that's not good. So you want to look somewhere here close to perhaps on the white 186 might be a good around. Look into that, into that RPM might provide you a good energy extraction. I'm not too happy with the number. They're very low in general. I mean, I'm talking about 13.6 meter per second, which is a breeze, but still, I don't know. They are way too low. I mean, 30 watts. Think about a solar panel. A solar panel. I mean, a drum. How much it costs a drum? Drum, pretty much you can get it for free, but still, the mounting and getting all that together that can resist the proper wind speed, like shown here, on terms of amount of wood that you have here to get this contraption ready to get some capture some of the wind. It will end up costing about, I don't know, like about $200 or so. Now, for $200, you can get hundreds of watts from solar panel, and I don't know. I think this is not a good idea to design something like this. If you can get your hand on a solar panel that might produce a lot more energy, very simple, and than using this Savonious type of wind turbine. Anything else that I have to say here? Let me see. Going back again to Solidworks. I think anything else here? Computational domains, basically the wind tunnel, nothing there. Environmental pressure is this wall. The inlet velocity 13.6, and the torque. The torque is basically measuring the force size of this Savonious turbine. Nothing more into it. I talked already about the global mesh and the local mesh. The global was left at 3. The local mesh was increased to about 5, from a maximum to that would be 9. I discussed the result, the cut plot, which again are producing something very interesting, which I have no idea. Show, you see, that red is very high speed, although the wind coming from this side is about 13.6. How I get wind that high, it beats me, no idea. But it's predicting very high winds. I have to check this wind tunnel again, perhaps gonna make this wall farther away because I think it might be creating problem here. So I don't know. But something is telling me that there's something fishy happening here, which is not clear to me. How can I get that wind so high within the turbine? Well, in the vicinity of the turbine, because in the vicinity, it's not within the turbine. The turbine is very small wind, like about, I don't know, A or so, as shown here in the blue, strong blue. But how I get this red, the yellow, and the green, which will be somewhere here. Wow, even up to about 80 miles an hour inside. I don't know. That's very, for me, that's very interesting, and I would like to find out why Solidworks is predicting that condition. I don't know. That's something that I need to check on that and keep doing a little bit more of flow simulation. And but again, the first thing that I will do is increase the tunnel box length. Instead of 4 meters that I have right now, I will increase it, I don't know, to about 8 meters and see what happens. Meaning, if I increase it, obviously this is going to take a while doing the iteration and so forth. Well, more than enough. That's basically it. Thank you for watching and have a great day. Bye. Alright, so I was about to finish this presentation, and it still bothers me why such a high wind speed, well above the 13.6 mile per hour that is coming from this wall hitting the turbine, in this case the Savonious. The Savonious is spinning at 242 RPM, so it's creating huge wind speed, way up, close to almost 100 miles an hour near the vicinity of the turbine. So I decide this time to go to the rotating region and put that number in 0. So now the turbine is not allowed to rotate. In doing so, I want to figure it out whether I still have higher speed, than the 13.6 on the wind tunnel that I have here. And so the first thing that I did after running at 0 RPM is check the flow trajectories, and they looks more decent now. I mean, makes more sense. They are going in one direction. You can see the flow going from the high speed zone, this is 13.6, down to the low speed zone. And now remember, the turbine is 0 RPM, it's not spinning. So when I put that on play mode, you can see there's a kind of weird condition happening right inside here. You can see the wind getting in, some of that is sliding in the inner part of the blade, and it's coming out by at the wall here. You can see it's coming and creating also now a turbulent region, like a vortex region on the second blade as shown here. And true, there's some higher speed than the 13.6 right here at the around the vicinity, but never in the neighborhood of what I saw when you allow the turbine to rotate. In this case, it's not rotating, but yet I'm getting wind speed above the 13.6, which is the one coming right from here. As you can see, this yellow color is somewhere here, and I'm getting some red, as you can see, on this side and this side. Better to watch this perhaps is on if I set this on, let's see, let me hide this for a second and let me go back now to this cut plot. Let me show. I like to show both of them. This is in the y direction, and now you can see definitely there's some red color here, which is somehow uh, high speed, about 15, 16 miles an hour from the wind that is coming here on this zone, which is about 13.6. And let's put the other plot as well. Show. All right, this is in the X direction, so you can see pretty nicely how the wind tunnel looks in the inside for the turbine that is fixed. We are not allowing the turbine to spin, and that's why you see it right there. And so when the wind's coming from this wall down here, you start to see some green color right out here, and very low wind speed, about in the neighborhood of less than 3 miles an hour nearby. And but now I would say few feet above the turbine, you start to see this red color, so it's higher speed, and so on the X direction, and so in the Y direction. So yes, you see higher wind speed than the one coming because of this turbine effect. It's not spinning, so that's the interesting part. It's not spinning. I can go, take a look here, and you can see a lot of red there, meaning that there's a high speed there, and coming down, and that's basically it. Hard to see on this one because I have to turn the figure upside down, but I'm gonna leave it right there, more or less. So again, we have some higher wind speed. So if you allow the turbine to get some speed, some RPMs, then we have very fast wind speed, which to me is, I'm not sure whether it's something that is due to the type of analysis that I'm doing that might not showing correct. However, with the turbine in the 0 RPM, I'm still getting higher wind speed than the one coming from the wall. And so I guess that this is it. I mean, this is one thing that I missed to show you when I was working on this. So I stopped and say, let's do this one at 0 RPM to figure it out what will be the outcome of this scenario. Can take a look this way as well. Kind of interesting. So wind coming this way. Let's get this here. So wind coming, and from here at 13.6, it hit the turbine, and then you start to develop this kind of a slow speed wind profile here, and then you get a little bit higher, around 4 or 6, then you get into the green, and then you get into the yellow, and finally you get into this kind of a red color, which will indicate somewhere between 15 and 16 miles an hour for a turbine that is not actually spinning at all. So, well, that now, yes, this is it. Have a great day. Bye.